Thank you very much. I want to bother you with this. So I will do a short presentation, and also mainly because I have another meeting at 11. Okay, I'm going to introduce this project that is called Experimental Assessment of Fast Quantum Key Distribution. It's a collaborative work between the Universitat Politécnica de Catalunya in Barcelona, Spain, and University of California, Davis. It's a project from the third call, took place between the 1st of October of 2021 to March 31st, 22. The objective of the project was to demonstrate experimentally a quantum key distribution method that we developed based on artificial intelligence that we develop in a simulation environment. So the collaboration between the two parties was very clear. We were providing, let's say, the intelligence, the software, to do a sort of A-based polarization distortion compensator model. That is, I will explain a bit about this in the next slide. And we could demonstrate this experimentally, its feasibility by means of using the testbed that was provided by the UC Davis team, with all not only the devices, but also the instruments, the lab instruments necessary for doing the measurements and for doing the configuration of the devices. The impacts of this project was, the expected impacts at that time was to facilitate the deployment of quantum key distribution systems by reducing the cost, because by using this piece of software, we can improve some bad effects with a reduced cost, and also because it simplifies the hardware defined. And also one of the expected impact was to establish, to set up this US experimental quantum communication laboratory to be exploited in coming projects, or in coming with coming research studies, even innovation if possible. So basically, our contribution from the more technical point of view was to improve quantum key distribution, just as a 101 introduction of how this works. Quantum key distribution uses a quantum channel to distribute keys, secret keys that then are used to encrypt some data that is sent in a public channel. This is secure, inherently secure, because whatever eavesdropping action that is done in the quantum channel, because of the quantum physics, at the end we are sending photons or weak pulses that if are intercepted by an eavesdropper, they are lost unless the eavesdropper introduce again that signal. And this signal cannot be introduced in the same way that the transmitter does, because the transmitter takes some pure randomness at generating this. So at some point, the receiver is going to detect that there is something there, and is going to interrupt the transmission to keep the security. The point is that not only the eavesdroppers are introducing these distortions in the photons that are detected as a bad thing. For instance, environmental events. Most of these fibers are not varied, are aerial cables, but even in the varied cables, there are some polarization distortions. The quantum bits are, at the end of the day, are implemented as polarized photons that travel the fiber. If whatever thing changes the polarization, then that qubit is some way corrupted. So some environmental event, high wind, different radiation, even temperature can change that. And one way to correct this is to use artificial intelligence in the quantum receiver, because this type of distortions that are not made by an eavesdropper but an environmental event are typically predictable. They follow some pattern in the state of polarization. So this is the way we distinguish between one and the other. We had these algorithms that we presented in a journal paper with some engines that are working at the receiver side to do this correction in the state of polarization in the compensator part to compensate any state of polarization change and keep the validity of that keys that are transmitted in the way to increase the rate of exchanging these keys. So this was our input to the project, our what we could provide, our software testbed, let us say, and this experimental setup that we could develop in this project that was in the UC Davis lab. Uh, where we could design with the conceptual architecture that was foreseen for this use case and for this software, we could implement this using the hardware that was available in the lab of UC Davis. Here there are some pictures. Yes, I'm going to skip all this part. The good point is that, okay, we could validate in the deliverables of the project, there are all the measurements that we did, the validations that we did of the algorithm, and that was the primarily objective of this work, but also we got a lot of insights from the project because of we discovered how difficult it is to work with hardware. Uh, uh, Mainly when we are working in a quantum world, we decided to go go a step forward, and instead of putting simple A-based algorithms in the receiver, to build a digital twin, a quantum digital twin that get information from the current hardware and analyzes in more detail what can happen. And this includes, for instance, tuning the hardware devices in order to improve some imperfections that hardware devices can have. Before this project, we were assuming some sort of ideal hardware, but now we discover that the hardware is not ideal at all, and it's very sensitive. So we need to do something for making this operative in a real world, and this something else. And this is this digital twin that we name Darius, and we are working right now on this digital twin. And this we started working on this thanks to the outcome of this project. Also discovering that you cannot manage simple artificial intelligence models, for instance, just a single neural network that is able to correct everything that happens. Now we need to have different models that run in parallel, and also that digital twin that is doing a more high level analysis and decide, okay, now we are entering or we are having the situation that requires using model A, and now we change and better use model B. For instance, for the magnitude of the events. It's not the same working in a regime of low to moderate sub events, state of polarization events, than moderate to high ones. No, and we need something that can supervise this and decide which is the best model that can be used at every time. And also, this was an outcome of the project. As a exploitation, dissemination, and communication results, well, we published an ECOC paper that is one of the main conferences in optical communications in Europe, as a presenting the experimental results. Also, we published an open research data set containing the main measurements that we took in the project. Also for the research community to have measurements of real devices that can be used for other quantum like or quantum-based use cases. Also, we had different outreach in Twitter, LinkedIn, as well as teaching some of the concepts in undergraduate courses in the university. Well, in this case, for master degree in cybersecurity. Basically, as I told you before, this project gave us a lot of experience of how to deal with all the problems that are in the equipment. For instance, to reuse all material or all equipment that, in principle, theoretically can work for a quantum scenario, but because of they are old and they are misconfigured, they have some imperfections that could work for normal classical optical communications, are not suitable for quantum communications, or at least require much more fine tuning and also some continuous supervising of that tuning to retune if necessary. Because of there are very scarce data related to quantum. We think that this open data set that we publish is a good way to solve a bit this scarcity, because also can promote the new ideas and new use cases that can be applied. And also, this joint demonstrator is an starting point. We have a lot of the other use cases and other specific problems related to these quantum channels that they need to be experimentally demonstrated. And then we need to keep this collaboration in the future, from now and in the future, to have the possibility to check if what we can do in simulator can be validated in experimentally, or how we need to tune the simulators, how we need to add new sources of noise in our simulators, for instance, to match better the experimental devices. No? And well, this again, where one of the main outcomes was that we need a digital twin, something more complex, and we are working on that. And precisely, we have recently submitted a paper in a GLT about this digital twin, extending what we did in this project. And also we are participating in other projects currently that want to exploit some of these potential use cases for the digital twin. But we need to continue with that collaboration, because the experimental data set that we had with UC Davis, is really good, and I think that we can potentially exploit in a future. Well, main outcomes, this ECOG paper. Here you have the references. Here also you have the reference of the open research data set and the contact points, Luis Velasco or myself in UPC, and the team from Professor Benju in UC Davis with Sandeep Kumar, for instance, or Roberto Proietti that now joined Polito, but also can solve whatever question about this thing. So, well, thank you very much for attending, and if you have any question, we can discuss.
Thank you, Marc, Ruiz. I know you have to run off to another meeting, but just
yeah, but I can have 5 minutes more, no problem.
okay. Just I wanted to point out, as I mentioned yesterday, there's some new NGI projects in the NGI family that you might want to look at. There's one called NGI Zero Core, which is looking at the internet architectures, including quantum and things like that. So, and then just a quick question about the US partner. Like I asked earlier, did they provide any feedbacks on any challenges that they encountered with the funding landscape from the NSF or anything like that?
From this project, not for I don't know for next calls, but at least for this project, what I'm not sure, or I don't remember very well, but we had this sorry, wait a moment. We had this they applied. I think I think that they didn't give the funding or additional funding, because also that group has also some funding for other NSF projects, because it's a large group, and also with a very nice test beds, and also I mean they are also participating in other projects. Also they have experience in asking for them. My feeling is that they didn't find any additional, let's say, difficulty from the ones that they also have. But honestly, I don't know more about this. But what I can tell you is that they when at the time that was expected, no, they could apply was when it happened. They applied, but they don't get any additional funding, but maybe because of this, maybe because they have also more fundings for other projects or.
Okay. All right, thank you. Jorge?
Well, just a quick question to let you go to the other meeting. You mentioned several plans to continue the work that you are doing. Are you still collaborating with UC Davis in the future, or now based on these contacts, or you need more funding in order to continue the collaboration, or how do you foresee the future with them?
Yeah, we need more funding because it's the point is that also this collaboration was not started. I mean, the collaboration with that group was not started in this project. We had a collaboration in other topics related to optical communications in general. This was our first collaboration in the quantum, let us say. And we gain a lot of, I mean, basically what we did is to do an initial setup of everything working. No, now is where we can start doing more interesting things, because we can, for instance, test this digital twin that is much more complex in terms of the algorithms, but it's much more complex, needs that you need more equipment, and you need more, even also have the people there. Dedicate time to perform the experiments is not easy. Finding how to configure, how to calibrate the digital twin from the measurements is something new. Just in this project, with just a couple of parameters, we had a lot of problems, and now with the digital twin that has more tens of parameters to tune, it will be much more difficult. And yeah, we need a specific funding for specific projects on this, and for sure, I think that this is a key topic that we should explore in next calls for sure.
Thank you. Good luck with your next meeting.
Thank you.
Thank you, Marc, Ruiz.